In this problem, we are going to combine things that we know about unbalanced forces with our previous constant acceleration model to really describe the physics of a situation. In this problem, a car accelerates from rest so that it travels 30 meters in 7 seconds. While accelerating, there are 700 newtons of air resistance acting against the car. The car has a weight of 2,700 newtons. And the problem advises us to draw any useful diagrams or graphs and use these to find interesting unknown quantities. We're going to combine graphical representations from our constant acceleration model with force diagrams and other things we know about forces to solve this problem. So I'm going to take all the information that I know and I'm going to put it one of two places, either on a force diagram or on a velocity versus time graph. So starting with a car accelerates from rest. Rest tells me that when the time is 0 seconds, the velocity is 0 meters a second. The car is going to accelerate, so its velocity is going to increase. And it accelerates so that it travels 30 meters in 7 seconds. So I'm going to label 7 seconds on my velocity graph, and 30 meters is a displacement, which on a velocity graph, as a review, displacement is the area under the curve. So we know that's 30 meters. We don't know the final velocity, so I'm just going to label that with a variable VF. While accelerating, there are 700 newtons of air resistance acting against the car. Well, newtons, that's a force. That's going to go on the force diagram. So I'm going to start the force diagram for my car. I'm going to assume that the car is on this planet, so there's a force of gravity that the entire Earth applies to the car. The car is probably touching the ground, so the ground will apply a normal force to the car. The car is accelerating, so something must be pushing it forward. That would be rolling friction that the ground applies to the car. And it does say that there's air resistance in this problem, and that's going to be going the opposite of the direction that the car is moving. So we have the force of air resistance that air applies to the car. And on this force diagram, the forces that we know that air resistance is 700 newtons. We know that the weight of the car is 2,700 newtons. So we've drawn all the diagrams that we can. The next, we want to use these diagrams to write some equations so that we can determine some interesting unknown quantities. We could write net force equations for the car. So let's start there. For the car, in the x direction, the force of rolling friction minus the force of air resistance is unbalanced because the car is accelerating in this direction, so those forces are going to equal ma. And in the y-axis, the car is moving, it's not moving up and down, so it has a constant velocity of 0, and the net force will be 0. So Fn minus Fg is equal to 0. If we use our velocity graph to write some equations from our constant velocity model, we have a couple of things that we can exploit. We can use the area under the curve, which says that displacement is equal to 1/2 VF plus VI times time. We can also use the slope, which says that acceleration is equal to VF minus VI over time. At this point, we have identified the math relationships that we can use to solve this problem and figure out more information about this problem. Next, we have to decide where to start. Acceleration is the go-between variable. That's the only thing that is common among what's called the kinematic equations, the equations describing motion, and the dynamic equations, the equations that cause motion. So A is kind of our go-between variable, and right now we don't know acceleration, but if we could figure out acceleration using either the motion equations or the force equations, we can use acceleration and translate over to the other side or the other model. To decide which model to use first, I'm just going to look at what I know. In the kinematic side of things, I know displacement, I know initial velocity, and I know time. So this would be a good place to start. I could figure out my final velocity using the area under the curve. Once I know the final velocity, I do know time and I do know initial velocity. If I figured out final velocity, then I could find acceleration. So I think I'm going to try that as my first strategy. Again, sometimes, some problems you'll start with the force equations, sometimes you'll start with the kinematic equations. It just depends on what you know in the problem. On the previous slide, I strategized that I wanted to start with the kinematic equations because I know more information there. So I've already written the model I'm going to start with. The displacement was 30 meters. The area under the curve was shaped like a triangle. And my final velocity, I don't know, but my initial velocity was 0. The time is 7 seconds. So if I do some algebra here and solve for final velocity, I found that the final velocity is 8.57 meters for every second. Once I have the final velocity, I can use the slope of my velocity versus time graph to figure out the acceleration, because slope means acceleration. In this, I'm solving for acceleration. The final velocity I just found was 8.57. The initial velocity was 0, and that change in velocity took place over a period of 7 seconds. So the acceleration for this problem is 1.22 meters per second each second. So the velocity increased 1.2 meters a second every second. Remember, acceleration is my go-between variable, so I can now use acceleration with some of my force equations to maybe figure out more interesting force information. I'm going to now use one of my force equations. This is the net force equation that I wrote for the y-axis for the car. I was actually given the weight of the car to be 2,700 newtons. And because the only other force acting in the y direction is the normal force, and the forces in the y direction have to be balanced, the normal force must also be equal to 2,700 newtons. I could have started with that equation just as easily. I knew I didn't need anything I got from the kinematic equations to solve that, but it was just what occurred to me next. If I do the x-axis, there are two forces, the force of rolling friction minus the force of air resistance. And that axis was unbalanced, so the forces add up to mass times acceleration. I do not know the force of rolling friction, but it was told in the problem that the air resistance was 700 newtons. I know the acceleration of the car, I figured it out using kinematic equations, was 1.22 meters per second each second. Now, I don't know the mass of the car, so I need to figure that out, and I can go off to the side and use another relationship that I know to figure out mass. I know that the weight of an object is equal to its mass times the acceleration due to gravity, so in this case, I know the weight of the car was 2,700 newtons. So the mass must be 2,700 newtons divided by 9.8. And it looks like the mass of the car is 276 kilograms. So I can use that here. So now I have enough information to solve for the force of rolling friction. And I find that the force of rolling friction is 1,037 newtons. So I've now solved for all of the forces on the force diagram. I could go back and label them on my force diagram if I wanted. I've solved for the acceleration. I've solved for the final velocity of the car. If I really wanted to convince my teacher that I knew more about physics or describe this problem in more ways, some other things that I could do is I could sketch a position versus time graph for this car. I know that the car traveled 30 meters in 7 seconds and the car's speeding up, so its position graph's going to be shaped like a top open parabola, and I'll label as much as I know on it. In 7 seconds, the displacement was 30 meters. I could also draw an acceleration graph for this car. The acceleration of this car is a constant 1.22 meters per second each second. If I really wanted to go crazy, you could even draw a motion map for this car. So in doing that, we would actually have combined everything that we know about physics for this whole chapter into just one problem. You'll have a chance to try a couple of open-ended problems like this yourself. Hope you can be creative and solve it in as many ways as possible.